In the previous video, we saw one possibility that can happen when we have repeated eigenvalues. Here we're going to see another one. We have the system dx dt equals 3x plus 2y plus 4z, dy dt equals 2x plus 2z, dz dt equals 4x plus 2y plus 3z. I'll let you confirm that when you find the determinant 3 minus lambda 2, 4, 2, negative lambda 2, 4, 2, 3 minus lambda, set that equal to 0, you get lambda equals 8, negative 1, and negative 1. In other words, negative 1 is repeated. Lambda 1 equals 8 is associated with an eigenvector that I'll call k1, and it gives us 2, 1, 2. Again, please confirm that on your own. My focus now is for the eigenvalue lambda 2 equals negative 1. Plugging that into our A minus lambda I matrix gives us 4, 2, 4, 2, 1, 2, 4, 2, 4 times k is equal to 0. You can see that these three rows are multiples of each other. And so they really boil down to 2k1 plus k2 plus 2k3 is equal to 0. We can't let them all equal 0, but we can let any one of them equal 0 and thereby get a relationship between the other two. Suppose we let k2 equal 0. Then we have that k1 is equal to negative k3, and that gives us an eigenvector of k2, I'll call it, equals 1, 0, negative 1. Then we can let either of the other ones equal 0. Suppose we let k3 equal 0. Then we end up with 2k1 plus k2 is equal to 0, which gives us that k1 equals negative 1/2 k2. And if we let k2 equal, say, negative 2, then we have the vector k3, which is going to be 1, negative 2, 0. These two vectors, k2, which is 1, 0, negative 1, and k3, which is 1, negative 2, 0, are linearly independent. That allows us to immediately form our solution without invoking a Jordan chain or anything like that. X of t is equal to c1 times 212 e to the 8t for the first solution that we got, plus c2 times 1, 0, negative 1 e to the negative t from k2, plus c3 times 1, negative 2, 0 e to the negative t from k3. That's our solution. And folks, that'll happen when all three rows of our matrix boil down to the same equation.